So, welcome again. Can you start now? Okay, so now we have so far discussed about the methodology and technique for equalizing molecule, how to optimize it, and how to derive energy. But so far, have you seen anywhere I have put temperature? Any slides have you seen any temperature part was there in the construction of Hamiltonian, in the construction of function, in the potential energy, in the kinetic energy part? Anywhere temperature was there? So that is one of the drawback, is it not? That is one of the drawback because in practical life, everything is, we always discuss anything about in room temperature. Or whatever that is, whether it is a DFT part, so far I have discussed in DFT or HA or HFO. Nowhere I have included temperature. So that means what you are getting all are in 0 K. Okay, because quantum phenomena disappears at high temperature. Is it a quantum phenomena is basically what I say 0 K effect in general. Okay. Because the energy is so small that at room temperature that effect goes up. Okay. Now, but we are always interested because you have you are using DFT, you are using Hartree-Fock fine, you are getting a molecular, and then you are trying to verify your data with experimental. So then the level is not same, is it or not? One you are using a 0 K. Or you are comparing that room temperature. So that is not a level playing field. So you have to level playing field. So what you have to do, we do for structure we cannot do. Is it or not? Because we cannot anyway we can input temperature in the your Hamiltonian, but we can do. But later on, like tomorrow if time is there, I will discuss. In Fermi-Dirac distribution, you can input temperature in the Hamiltonian basically. Okay, but people rarely follow that because the temperature does not have much effect on texture, on geometry. So based on that assumption, we say that since temperature does not have much effect on that, suppose if you are a water, you are having a water, and water if you take the normal water, if you is bond length, if you measure it, if you measure the water bond length in vapor, you want to expect that its temperature it change. Or if you want to measure the bond length of water in ice, it is -4 or something, isn't it? If you want to, you will expect the bond length of oil to get changed much. It will not change much. Okay, so based on that assumption or our practical experience, we can say the temperature does not have much effect on the geometry. Okay, but temperature does have effect on energy. Okay, not only that, even many things we decide not by energy, we decide by enthalpy or by free energy. So now if I get some energy from the DFT or HF, how to improve thermodynamics in that part? Okay, so there is a recipe for that. Basically, we use the ideal gas approximation. What is the ideal gas approximation? Again, we are using the classical concept here. We are using the classical concept that is degree of freedom is having a value of 50 or RT, you can say that, or per mole. Okay. So now I will come to that part that basically DFT or JEA, what I say, Hartree-Fock, we are calculating this E. That we already know. At 0 K, we are calculating this energy. So now I want to calculate the internal energy. So what I can do, I can add 0 point energy correction. You know what is 0 point energy? The energy at 0 K. Is it or not? That is why it is 0 point energy. Is it or not? So 0 K energy. And then I do the thermal correction. How I can do the thermal correction? I can put this value. That translational, there are 3 degrees of translational motion and 3 degrees of rotational motion. So I can add, but rotational for nonlinear and linear molecule will be we have for 2. So I will get only RT. As for nonlinear, it is 3/2. So if I add this to 3/2 plus 3/2, I can add this here. So now I started with my energy. I will do the 0 point energy correction. I will get the value. 0 point energy value is nothing but half h nu. Half h nu. So how do we get that new? Already I have told you that if you, when you are doing the Hessian calculation, you are doing basically force calculation. The force calculation, you know that from the force nu equal to 1 by 2 s by root over k by m. So from there you will get your nu. So you know the nu are already H Planck constant. So you will get the 0 point energy. So basically I have got thermal correction from the ideal gas approximation and the 0 point energy. So I am getting my internal energy.
You know that atomic migration, like because the at 0 at Kelvin, there is no molecular migration. Oxygen. Considering the fact no kinetic energy within the molecule because the temperature is so low. When hydrogen is not able to migrate at 0 Kelvin.
So you are explaining in terms of motion. Okay, basically that's okay, but you are explaining, but you are not giving any expression for that. So I have to give us an expression for that. That is not. So you know that E equal to n plus half h nu. Is it or not? So at 0k, your vibration at will be in the lowest ground state, n equal to 0. That is the condition of 0k. Is it or not? So then your n will be 0. So basically you are leading to E equal to half h nu. So that is why it is called 0 point energy. Okay, fine. So now you have got your internal energy. So now if you add PV, how you get enthalpy? If you add a PV means work done. If you add work done with that, you will get your enthalpy. But since I have told that I will use the ideal gas approximation, so in ideal gas approximation, this PV is nothing but del nRT. Okay, so del nRT, I will keep it nRT because when you do a reaction, it will be changed to the number of change in mole. Okay, so now you know your enthalpy by this ideal gas approximation correction, and then you know this equation gives free energy. This is nothing but the enthalpy minus T of S. Now, still I have used from the computation this guy. This I have taken from this correction. Okay, here also I have taken this correction. Now I have to calculate this 0 point energy that I have already told how I can calculate from the computation. And now here also you see that G equal to H I have got already. How to get T, S. Okay, so S how to get from the computation? We will take the help of statistical thermodynamics. So it is there. If you see that we can represent the partition function Q in terms of cancellation and rotation and vibration. Okay, for cancellation and partition function is written like this. Okay, for vibration it is this. I am not going to the derivation of those, and for rotation it is this. So for using this relation, those who are aware of the statistical thermodynamics, there is a relation for calculating. This is given by the Sakut tetrode equation. It is called. So S is equal to KLN plus this, okay, derivative of this. So you will get, if you all Q you know already. So you just have to do some mathematics and you will get the contribution from cancellation and contribution rotation and contribution. So I have got now my all entries I have got. So my destination was free energy. So now I have got enthalpy. Now I will go there. All are printed in your either it is a Gaussian, it is a thermomol, it is a Orca, whatever, or every software is a standard package for this, so you will get this. So now I have got my entropy, so I will get the free energy. So this is a simple example. Actually, I have used a very long back that I just structure part I was talking about it. So if you see that this is I think 1.25, this is experimental result, I think, and it's a computed result. So they are very close. So that means you see that. Coming very close, so then the temperature, just presuming the temperature doesn't much effect on that. Okay. And then, as I told, how to calculate the interaction energy, just Jogandro was asking that how to hydrate and water. So you can just here we have taken, suppose you one molecule, I have taken one ion. I think that ion is, I think, this. Since I am from VRC, so we work on extensively on this and lanthanide actinide because the nuclear fuel after burn up whatever is there, you have to separate again and you have to use it. So for that we used to use this computer then. So this is the thing. So basically they can go if it's a 1:1 complex, if it's a 1:2 complex, 1 metal ion 2 ligand, 1 metal ion 3 ligand. So how that energy is getting changed, that I have shown that. That's what I want to say. Give an observation. That if you do the experiment also follow the same. With increasing ligand concentration, your stability also will go up. Those who are from the chemistry background, they know that there is a term called successive stability constant. And if you multiply the successive stability constant, you get the overall stability constant. So same thing you can do from the computation also. Okay. So now the same thing what I just show you that I did the correction for thermodynamics. So enthalpy I have got, then entropy I have calculated, and from there I have calculated free energy of change for that compensation. So basically, if you know that free change in free energy, you can calculate indirectly the equilibrium constant also there by equating del G equal to minus RT K. Okay. So when you can do varieties of computation, variety of calculation for your experimental data also. So how you so beautifully the computed data can validate your or rather I say complement your experimental data. So now this what that earlier the example I have given you the structure for water, benzene, then water. For that all system I calculated energy, 0 point energy, 0 point RT, then H, enthalpy, entropy, free energy, just to use to see your view about it. And then free energy calculation for this reaction. This is and this I think this is for B3 leaf TGP. I just wanted to show that though there is no much change in the structure, you'll see that there is a change in the energy. Here it was positive showing, but after taking the basis set here, it is B3 leaf TGP, I think that has become negative basically. So basically, it is very important that to accurately calculate the thermodynamics, you have to go for a better basis set actually. So basically, that means you have to be very careful about what system you are studying, and when you are going to compare to the experimental result, you should assure yourself that you are taking care of good functional as well as towards complete basis set. So I am not going to details because thermomol we are not giving hands-on session. This is for thermomol; those are using thermomol. I am not going to details. Then I just want to share another thing. This is called, I'm not going to take the details, but basically if you want to calculate the, suppose somebody was speaking about a 2-phase or 3-phase system. Suppose you are having one ion in water and that water is getting extracted in the organic phase. Okay, for that I want to calculate the hot to the free energy, the ion will move to the organic phase. For that I can calculate the free energy of extraction. Okay, so for that I just I have calculated and I can say this is the experimental result actually basically that I have showed here or not, I just don't understand. This is absolutely. So basically, this is selectivity. This is europium and americium. So basically, in a nuclear fuel cycle in the reactor, basically these things are getting generated, europium and americium. So you have to separate them because one is highly radioactive. This both are having a separate use. So you want to use separate use of the both. We have to separate it. So we are doing some computation to come up with a new ligand. So in that case, this theory is giving this high value experiment. But overall, what is it? Because the theory is a highly approximated theory, is it or not? In case your experiment, already the system is radioactive. I have not taken any radioactive part in my calculation. Already system is radioactivity. Now system is highly condensed phase. Condensed means they are continuum phase, is it or not? I have taken isolated system. So that way also it is giving the correct trend. But our objective was not to give the absolute value, to just capture the correct trend because I want to, so I am having a multiple ligand, A to Z. I just want to compare. So there is no harm in comparing because that error what is coming through my computation that will be nullified for all the cases. So you can come out with a trend. And in that trend, you can say that you go for this ligand design and you use for application. So that means thermodynamics can be very helpful. DFT-based thermodynamics, you can say, is very helpful for supporting the experimental data and that in highly radioactive environment. Okay. So then you can calculate those who are somebody was talking about the toxicity. Is it or not? Toxicity is basically nothing but the molecular interaction. Is it or not? So a toxic molecule, when you go to your body, it is binding to some your other body part. Is it or not? And that body part, you can. This is nothing but interaction. Is it or not? The interaction is strong or weak. So you can capture from this electronegativity or electroaffinity. Okay. And then some people, I think, Professor Banerjee and the Devasys school, they will be talking about Cosmo, I think. So you can. So far, I have not considered any solvation with it. Okay, but you can use the solvation also. I have talking about the isolated system. Okay, gas phase. So now you can include solvation also using the Cosmo model is there that was a Banerjee will be speaking at. And then so far I was talking about this that so far how big a molecule you have considered it or molecular system you have considered it. So basically we have considered so far in our lab and the system consisting of 491 atoms and we have run it basically one of the we are having a supercomputer. In the supercomputer, it is called Atulla. It is a petaflop, is 2.86 petaflop. I think it is. I think in ISC they are having one. That is, I think first. I think it is more than 3. We are the second highest, I think. So we have used 240 processors and structure optimization. This molecule is takes actually this neptunium ion. This is also another radioactive ion, and we are trying to separate it with this benzene type of DZA. Okay, and then it runs for optimization only 19 days. This is 240 processor, 19 days. It takes for optimization. Okay, and then I have given the details also, and then Hessian calculation. We started, I think, January, March 29, something is supposed to have something is there. When I just wanted to highlight that if molecule is very big, it is so many local minima will be there. It is actually very difficult to optimize it. Okay, so this is the to get that feeling. I don't know how. That is why I was asking how big molecules so far you have encounter in your research. So you can tell me. Okay, so now now I come to the population analysis. Population analysis is nothing but to find out. So now you are having a molecule. Okay, suppose let us consider the water molecule is there. So oxygen is there, hydrogen is there. So how do we know? Oxygen will be minus 2 each will be plus 1. That is a concept, is it or not? But actually, that is you are using that integral chart. But when it will form a molecule, it does not behave like that. Is it or not? So that charge distribution, how actually in a molecule the charge will be distributed, and how do their bond, or suppose there is a double bond, a triple bond, pi bond, lone pair is there, how to calculate those? So for that, the concept of population analysis is come. Okay. So I think there will be a hands-on session by I think Raymond and Raghuval about that. So there are different kind of methods there. You see that Mulliken, I think many people are aware of Mulliken population analysis. Then NBO that I will talk about now. Then atomic molecules, KLPG, ANK, means Marge and Coleman. And you can calculate homo, you can calculate molecular electrostatic potential. Yes, you are talking about your for toxicity. It's very important because molecular electrostatic potential, from there you get the charge distribution. Okay, so how the charge density is very electronegativity, there will nucleophile will come and attack that. So toxic molecule will go only toxic. When a molecule is toxic, it will not go and sit everywhere. So it will go from sites and it will sit there. So you can find out the site from the MD as well as DFT combined combination. You can find that. So you can identify the toxic site, and you can accordingly even design. Those who are working in docking, they can design that if I generate another molecule which prevent that site to attack by the toxic molecule. Okay, so this is you can have bond critical point. Suppose you are in a bond, so where is the electron density is basically more concentrated, that you can calculate from the bond critical point, and also you can calculate the shape of the orbital which are participating in your molecule. So the natural population analysis will give all kind of information, basically what basically chemistry are interested. So molecular population analysis, I will just give a bit details. The molecular population analysis, what it does. This is a very simple thing, and people think it is very complicated. Already I have shown you that how molecular orbital is constructed. Is it or not? So it is basically I have shown you the some coefficient and atomic orbital. Is it or not? So now that and from that if you do the integration, you get the total number of electron. Okay. So basically what you are trying to do, that I know that I have constructed the function, I have constructed the orbital. I knew already that what my electron is there. Again, I want to recalculate how when I have put them, what is the distribution they are there. And now I have got my true wave function. If I thinking that I have got my true wave function, how those electrons are distributed. Basically, that is the now our objective for population analysis. And then if I know that there the number of electron in this orbital is this, in this orbital is this, and from there I can also calculate the charge also. Okay, so that is the fund of that. So now what I was discussing. So now I can get the number of electron here. So this Ni is the number, is the basically occupation number each orbital using the Pauli exclusion principle. So then you can you can see put it here, this value, put it here, and then you can rearrange this and you can rearrange this coefficient in terms of this. And this is nothing but n equal to n. So basically what you are trying to the number of your concept is now that I know my total number of electron. I know that my total number of atoms. So now I am distributing that electron density in terms of atom. Okay, so that is the concept of Mulliken. So why Mulliken is going wrong, that will come to know why. Though averagely it works, but in accurate terms, it does not work. So basically, what he is doing, the whole molecule is there. Then whole I know already my number of electron, and then he is distributing that individual atom. Okay, so how he is distributing? He is telling that if I am having a similar type of atom, they are equally distributing the electron. Accepted. Okay, if similar people are there, they are distributing equally. But what he is doing, that guy, that if AB is there, A and B type atom is there, they are equally distributed. That is not correct. Is it or not? So then, using this concept, this and this, he is finally coming up that I am having similar type of atom, I am having a different type of atom, and finally he is approximating that as if all the electrons they are distributing different kind of atom equally. Basically, whether it is the same atom or it is a different atom, when they are forming a bond, the electron is getting equally distributed. So that was the follow of Mulliken. Then this guy came, Loudon. He tried to correct this part. I am not going to detailed derivation. So what he's put this orthonormality condition. Orthonormality condition means heard about the orthogonal and normalization. Orthogonality, if same type of orbital, that is called orthogonal, they will be contributing. And if the different type of orbital, they will not contribute. They will contribute 0. I equal to I equal to J, it is orthogonal. If I not equal to J, it is orthonormal. So that concept he is applied. Then he's come to know, he has nullified his concept. It is not same atom. It has to be, it is not a different atom. It has to be same atom. So that what was the flaw was there in Mulliken, he has corrected it. But only during doing this thing, he does some mathematics, and that mathematics was a little bit complicated. So that is why people do not follow the Loudon population. But still, though Mulliken is erroneous, but in the average for small basis set, it was very fine. Because small basis set, the atomic distribution, whatever is there, whatever the principle is there, whether it is the same atom or different atom, the distribution. But when it is a big molecule is there, so that principle does not work. So in the case, when you will go for a large system, you will go for a basis set, a bigger basis set. So automatically you will get a deviation from the Mulliken population from other accurate population distribution. I will come to the next now. Okay, so I'm not going to discuss about this. This is a very good thing. Atoms and molecules. It is very accurate enough, but I am not going to talk about it. Then Lewis structure. Why that natural bond order analysis is very important. Basically, as I told you, the Lewis given us the idea that you can write a water molecule structure like this. You can write a BH3 like this, NH3 like this, benzene like this. So it is for any kid. It is very easy to understand. So if you want to teach a kid, yeah, what is a bond? What is a molecule structure? So they will happily understand it. Is it or not? So the 2 eyes in top, 2 eyes in down. Is it or not? So they will enjoy the structure. So Lewis. So basically, what I mean to say, the representation Lewis is very good to convince a person about the bonding nature. Is it or not? About the presence of lone pair. Is it or not? So that is thing only I have written here. So now, in view, it is based in, as name suggests, it is a natural bond orbital. Natural bond orbital. Now, why the natural word came? Natural means by naturality. So why we are calling it naturality? When we are representing a wave function, when we are constructing a wave function, and that wave function is using the orbital, molecular orbital, for constructing itself. So if we consider my final wave function is the natural one, so automatically whatever the things he has used, so that I will consider it a natural. Because if I want to sell something that is a natural, then every ingredients of that thing should be natural. Is it or not? Then only you can buy a natural. So that is why the natural word come like this, that wave function what has been constructed, it has come by the construction of the wave function from the molecular orbital. So that is the name naturality. Okay. So now in this here. Now how we go from the molecular orbital? Basically, we have started from the atomic orbital that we have shown, but in between these things we have not discussed. Is it or not? This is called natural atomic orbital, the natural hybrid orbital, the natural bond orbital. So that is our interest was the natural bond orbital. That we have all the information, but we are not using it for our purpose. So now let us use that part for that information. Already during calculation, it is already generating, but we are not using. But if we are using it, it will be very helpful for describing the bonding of the system. Okay, fine. So now during that we will come across another concept that is called natural population analysis. Natural population analysis is nothing but that only it will tell you the distribution of charge when you are making a molecule. How earlier I was talking about in the water you are taking the integral charge +1 -1, but when you are actually calculating, you will see that electron does not behave like that as an integer number. So it will be fractional of that. Okay, so that is actually given by the natural population. When they will do the Helmut session, they will show how it looks. Okay. So now what I was taking that natural atomic orbital, natural hybrid orbital, natural bond orbital. I am not going to the details about the. It is there, so all you can have. I will give you the PPT if you are interested how that thing has come up theoretically. That is given. I will go to the directly to the yeah. Basically, you see that you know already how sigma bond is defined. That is sigma bond is nothing but head on. Is it or not? We define the bond head on. That is called sigma bond. Our pi bond is lateral. Is it or not? If you see that this is lateral, okay, and this is non-bonding electron. If you see that this is shows that this is the your bonding, and this is a lone pair is shown in terms of this orbital. Okay, and this if it is a sigma anti-bonding, you see that this lobe has come this side, and this is a smaller lobe has come inside. Okay, and this is a pi anti-bonding. It is see the diagonally it is showing, and if it is an empty orbital will be showing like this. And if you do the energy ordering, so energy of the orbital will go up like this: sigma, then pi, then lone pair, then q, then pi star, then sigma star. Okay. So now this I have not in the Gaussian. I have done the natural bond orbital analysis in ADA. But this NBO code, it is universal. Wherever you run, you will get the similar kind of thing output actually. So here I have just shown that if you have a CC pi sigma bond, the occupation is 2. That I was telling you, this occupation is 2. If you having a CH kind of pi sigma bond, occupation is 2. If you having a this is pi bond between carbon-carbon, occupation is 1.6. It is a pi bond of anti-pi bond. The occupation is very 6. So definitely anti-bonding means the electron density will be very less. Is it or not? And then I have shown that if you are having a carbon of 2s orbital here, okay, that is a core electron, and this is a hydrogen is a 1s orbital. So if you hybridize it, and this is a 1p orbital. P orbital already have shown that this is looks like this, and if you hybridize this, you will get a ordering of the electron distribution like this. How it is getting. And those you can picturize in terms of orbital pi 1, pi 2, pi 3. Okay, so those they think they will show you in the hand session. Okay, and now you can further you can from the output you can find out that as I was checking that core electron, it should be around 2. Okay, valence electron of carbon should be 1. It is showing that way. So you can say that it was when it was constructing the orbital and when the wave function has been created. And this all things was written there. So just then we tabularize. Right? So you can use this things for explaining or interpreting or bonding of the molecular system. Is it okay? So now then you can see that you can as I was telling you charge how to calculate the charge. The charge you see the carbon charge is there. So carbon and hydrogen charge is there 0.2. So you see it was supposed to be neutral. All are neutral supposed to be, but you see that they are not neutral. Isn't it? So hydrogen has become positive and this guy has become negative. So charge has been transferred from hydrogen to. So in your case, CO2 and H2, if you want to see that how charge is getting transferred, the CO2 is giving to water is giving to. So accordingly, you can design your system. Is it or not? So basically, then you can the valence electron, how many electron code is there. It means there's a virtual orbital. So in the virtual orbital, there is no population basically. So, and the total number of electron also you can see. In case of carbon, it is supposed to be 6, but it has now become 6.21. So how 0.21 has come because hydrogen has contributed. Because hydrogen is supposed to be 1, it has come down. So basically, this electron density has come from hydrogen to carbon. Okay, so this kind of information you will get when you are going to design and become a new molecule. Got my point? And then total, you can see that finally you have to match the total here also. The problem of Mulligan was that sometimes Mulligan was overestimated of that. So you are supplying it to an electron. It should not go beyond 2 electron, but in case of molecule, something goes beyond 12. Okay, so that is a problem with the molecular population analysis. But in NBO, that problem is not there because your wave function is quite true wave function. Okay, so now this is the thing. Then electronic configuration, you can do the reconfiguration of an electron in the S, in the P, in the 2p also, in the 3p also. So you can say that in which orbital is contributing how much electron. Okay, that distribution you can do. Then Lewis and non-Lewis, just I was discussing about the Lewis structure. So whether your structure is Lewis and non-Lewis, you see that Lewis contribution is 38 and non-Lewis contribution is 3.2. So basically my structure is Lewis. So then it's all bonding and pop out, is it or not? So then here also similar way we have seen that what is the contribution of the core electron, what is the contribution of the valence Lewis. So you see the valence Lewis contribution is very high and core also very high, or is Rydberg, you see that Rydberg is very low. So basically there is no electron in the Rydberg or virtual orbital. So what are the concepts we have developed throughout the quantum chemistry? It is not fraud, but it is a justified actually that we are able to generate our concept of even you can say that above principle is there. If you apply to above principle, that also it will follow here also. So then, what is the contribution of S? You see that the orbital contribution here S is 100% 4 electron. Now, when it is hybridization, if you see that the orbital contribution is 50% from these guys, carbon and carbon 50%. The contribution from 1s orbital is 35%. P orbital after hybridization is basically sp2 hybridization. So you the P is having the 63.9%. So it can give you the concept of hybridization also. What Lewis has used. So now I'll go to the end. Okay, so that is the end. So this is the your what I say references. You can use it. I want to acknowledge my institute definitely where we are. This is our BSc computational super computational lab where I was talking about that 2.8 petaflop is there. Another also I will that we have recently you have opened a society for atomistic and computational modeling. If anybody wants to be a member, you can contact Raymond and Logibul. And thank you. So this is the thing. So if any question, otherwise directly we'll go to the Simpson session. If any question is there, otherwise Raymond and Logibul, you can start. They can also start telling something before starting the. Yeah.
That if it's the energy change, electron changes, then they will move. And polarization creates.
Right. Right.
And the polarization directly or indirectly will not mold the picture.
If you see that, just I gave an example. If you take water in ice, that is 0, and then if you normal water, what we are thinking.